Hello, my name is Jacob Adkins, and my risk project this summer was on object classification with ReSkin. I worked in the AGI lab supervised by Ronak Baranji and Abhinav Gupta. So the motivation of this project was based on applications to dexterous manipulation. Dexterous manipulation is a very difficult task for modern robotic systems to accomplish. It requires taking information from many different sensing modalities and using that information for fine motor control. And I think we would all agree that as humans, one of the most important sensing modalities that we use is our sense of touch. And we see this a lot in the animal kingdom as well. Many animals have very poor eyesight, but are still very skillful at dexterous manipulation because of their sense of touch. Notably, we see this in raccoons. They have very, very skillful dexterous manipulation skills. They're able to climb, they're able to pick stuff out of trash cans, they're able to be rather annoying to us humans because they're very crafty creatures who are very skillful with their hands. But notably, raccoons have poor eyesight. And as we can see in the GIF, what the raccoon is doing is he's feeling around the table, he's feeling the vine, feeling the different grapes until he finds a grape that he wants to eat, and then picks it up and skillfully puts it in his mouth to eat. So it would seem intuitively obvious that we should enable robots to have some sort of a sense of touch. However, most modern systems that attempt dexterous manipulation only use vision and audio alone, often omitting touch. And we conjecture that this is due to the fact that there's not a viable tactile sensor on the market, a sensor that is cost-effective, durable, and also enables large area sensing, and provides enough information about object shape and texture to be useful for the dexterous manipulation system. So, what is our solution? It's ReSkin, which is a relatively new tactile sensor that is cheap, conformal, durable, and is available for large area sensing. ReSkin, how does it work? So it's composed of a elastomer that's embedded with magnetic microparticles, along with a circuit board that contains magnetometers that detect changes in the magnetic field. So when an object touches a ReSkin sensor, the elastomer conforms to the object, and thus that moves the magnetic microparticles. And this creates a change in the magnetic field, which is then detected by the magnetometers. And in a previous paper, it was shown that you can train a neural network to predict the force and position being applied to the sensor from this magnetic field data. So in this work, we want to show that we can use this B field data for other things, such as classifying object shape and texture. So in the RISC project, we conducted two different types of experiments, one for classifying object shape and one for classifying object texture. So on the first experiment, we equipped a ReSkin sensor on a 3D printed robot finger. And then we applied a fixed torque to different objects and collected the ReSkin measurements for use in training a mixed MLP network for classifying the object shape. First, we collected 3 different labeled data sets, which were used for training the network. The data sets were translation, where we would just move the object into different positions, translation and rotation, and then translation and rotation and change in the base axis. So there were 6 different objects that we wanted to classify. We had a star, triangle, clover, rhombus, and a hexagon. And then we created the 3 labeled datasets, like I just mentioned, where we would translate, rotate, and flip these around their axis to get different ReSkin measurements along different sides of the objects. And then we trained a multi-layer perceptron to classify the shape from the measurements. So here's our results from this experiment. The model was able to very accurately classify the objects on both the translation and the translation plus rotation datasets. For the third dataset, where we were changing the base axis, the classification was noticeably lower, but we believe this is probably because the dataset was not large enough, and thus the model was not able to get enough samples from each of the different sides of the object to distinguish between objects. And another important point in this experiment is that the robot finger did not have very large surface area. So we weren't able to get data from all the different sides of the object at once. And this is a reason that we want to have large area sensing in our robot systems, so that as we touch objects, we're able to feel them from many different sides, and to get a better internal model of what's happening in our. So this leads us into our next experiment that we did, which was texture classification. So first, we moved from the 3D printed finger to a Demanda's hand, and we equipped ReSkin all over the hand. So there, as you can see in the picture, there's 3 different fingers and a palm, all equipped with ReSkin sensors. And the goal of this experiment was to see if we can use ReSkin to classify different textures. So we tried various textures like cardboard and a silicone sponge and bubble wrap, and we wrapped these textures in symmetric balls that were all the same shape to see if it could tell the difference between the different textures. So here's the different textures that we used and the pictures of the balls. We wrapped balls in small bubble wrap, large bubble wrap, the silicone sponge material, cardboard, as well as a ball that had a mixture of all 4 of those materials. And then we had another ball that was just the plain ball. And then again, we trained multi-layer perceptron to classify the texture. Classification experiment. As you can see, the model had very high accuracy on both the sponge ball and the plain ball, with reasonable accuracy on the big bubble wrap ball and the cardboard ball, but much noticeably lower accuracy on the mixed ball. This makes sense because the mixed ball was by far the most confusing, as it had a mixture of all the different textures that we used. We're currently experimenting with LSTMs and other more advanced neural network architectures to see if we can get better classification results than we did from the MLP alone. As for next steps, we plan to conduct a larger scale object classification study using the Demanda's hand with ReSkin sensors to classify a variety of household items as seen on the picture on the right. Thank you very much for your time. I would like to thank Ronak Baranji and Abhinav Gupta for supervising me during this project, as well as everyone else at the AGI lab for being a constant support. Also, I would like to thank Rachel Burchin and John Dolan for organizing RIS and making this possible.